All right, so we're continuing to think about how to solve quadratics. And I've got one written here. Oops. I've got one written here that if you try factoring like we did last time, you just won't be able to do it. There's at least no easy, no obvious factoring that we can do here. But it doesn't mean that we're out of luck. We can play a little game that we're going to call completing the square. So we're going to develop this idea and then try it on this particular completing the square. Whoops. There we go. Completing the square. All right. So the idea of completing the square is the following. We actually saw our first couple of examples in the last video. We saw a similar situation. We saw an equation that had a form like this. It had an expression of a simple linear function of x squared equal to a number. We found those to be very simple to solve. So we want to see if we can write this thing, our x squared plus 8x plus 1 equals 0, in some form like this. So what we're going to do, let's see what this looks like when we expand it. We multiply x times x, we get x squared. We'll get plus kx plus k squared, which we can rewrite as x squared plus 2kx plus k squared, right? So k is some constant here, x is our variable. And we want to be able to write the thing that we have, in this case, x squared plus 8x plus 1 equals 0, in the form x plus k squared, right? Which means we should try to write it first like this, or at least that's one strategy. What does it mean to be written this way? This is what we would say a perfect square polynomial, meaning we can write it as a linear function squared, not the product of two different linear functions that we saw when we were factoring, but one linear function times itself, okay? The thing that has to be true in order for this to be the case, what this is showing us is, let's look at the coefficients, the coefficient of x and the constant term. Notice that if we take half the coefficient of x and square it, we get the last term, right? So half of that coefficient, the coefficient is 2k, so half of it is k, and square it, we get the last term, okay? So we want to see if we can write this thing, 8x squared plus 8x plus 1, in that form. And so here's the trick we're going to use. So we will take, the first thing we're going to do is move that 1 to the other side by subtracting it, right? We can take away 1 on both sides, okay? We're going to kind of leave that over there and forget about it for the moment. And what I've got now is an x squared plus an 8x. I'm in my head, I'm thinking that I'm looking at this right now. I've got just the first two terms, and I want to figure out what k squared should be, right? Well, I know what it should be. It should be half the coefficient of x squared. So I take half of 8, which is 4, and I square it. But of course, whatever I do to one side, I have to do to the other, right? So this is a perfectly legal thing to do. We're adding 4 squared or 16 to both sides, and now we've got x squared plus 8x plus 16 is equal to -1 plus 16 is going to be 15, right? The whole reason we did that is so that we could write it like this. This thing here, x squared plus 8x plus 16, we designed to be exactly x plus 4 squared. And you can check that that's true. Just multiply out what you've got. X plus 4 squared means x plus 4 times x plus 4. We get x squared plus 4x plus 4x plus 16, or x squared plus 8x plus 16. Okay, so now we're in that situation that we did very early in the last video, or I can just take the square root of both sides, and I get x plus 4 is equal to plus or minus the square root of 15. I subtract my 4, and I get x is equal to -4 plus or minus the square root of 15, right? Subtract 4 from both sides to get this. And so there are my two answers. Let's write them out explicitly. We've got -4 plus the square root of 15, or x equals -4 minus the square root of 15. Okay. So this completing the square method is a super useful one when we can't factor. And it's actually useful in a lot of places besides just solving equations. So that's mostly where we'll look at it for now. Instead of checking our answers by plugging these values back in, which we could do, let's do something a little bit different this time. Let's think about graphs. So here I have the graph of x squared plus 8x plus 1. This is the blue graph we're looking at. And let's make this a little cleaner. Get rid of the grid. And recall that we were finding when did x squared plus 8x plus 1 equal 0? Well, this will be when the y coordinate of this graph is 0, the output, right? So I'm thinking of x squared plus 8x plus 1, that's my function, x is the input. The output is what happens when you plug a number in. And this will be when the y coordinate is 0, in other words, the x-intercepts, right? These 2 points here, one's really close to -8, one's pretty close to 0. Well, if you look over here, I've computed our two solutions. -4 plus the square root of 15 gives me -0.127, and on and on and on. That is the x coordinate right here. They've rounded it to 3 decimal places, -0.127. And then the x coordinate, the x value, -4 minus square root of 15 is -7.8729, or approximately -7.873, which we can see is the x coordinate here. So solving that equation is equivalent to finding the x coordinates of the graph of that expression when the y coordinate is 0, finding the x-intercepts, the two places where it hits the axis. So there's a little visualization of our problem. Let's do one more example. Do one more. So let's look at 3x squared minus 5x minus 3 is equal to 0. So we have a little bit different situation here. Notice when I figured out my little map, right? This is what I mean by my map. It tells me how to choose my coefficients or choose the thing to add by looking at the coefficient of x. When I did that, x squared didn't have a coefficient on it, right? So my map only applies in the case that the coefficient of x squared is 1, which is not the case here. However, I can simply make that the case. It's perfectly reasonable to take an equation like this and multiply both sides by 1/3. So on the left, we've got to distribute 1/3 times 3x squared gives me x squared. 1/3 times -5x is -5/3 x. 1/3 times -3 is -1. And of course, 0 times 1/3 is 0. We're going to now play the same game because now I do have a coefficient of x squared that's 1. So I'm going to first add 1 to the other side. I'm going to get x squared minus 5/3 x is equal to 1. Now I want to look at that coefficient of x. In this case, it's -5/3. I want half of that. So that's going to be -5/6. And then I need to add that squared to both sides. So let's just do that. Plus -5/6 squared plus -5/6 squared. Okay. So on the left-hand side, I'm not even going to bother squaring that and figuring out. I built this thing very specifically so that I could take this number and add it to x. So in this case, it's x plus -5/6 or minus 5/6 squared. I know that that's going to work out. I'm going to check it in a second to be sure, but that's how I built it. Okay. I don't really need to do any extra work there. I just know that that's the thing that we did, right? We took half the coefficient and squared it so that we could write it like this. That number that we're squaring, k squared, is the thing we have x plus that in our parentheses squared. On this side, though, I do want to make this into a nice constant. So this is going to be 1 plus 25 over 36. Or, so that's going to be, let's do this off to the side. 1 is just 36 over 36 plus 25 over 36 gives me 36 plus 25 is 61 over 36. So I get 61 over 36. And I've got x minus 5/6 squared. I can take the square root of both sides. So I'm going to get x minus 5 over 6 is equal to plus or minus the square root of 61 over 36. Let's remember this as well. If I take the square root of 61 over 36, I can think of this as the square root of 61 over the square root of 36, or root 61 over 6, or I'm going to write it as 1/6 times root 61. I think I like that better. They're equivalent. So this is going to now look like, let's add 5/6 to both sides. And I've got x equals 5/6 plus or minus, and I'm going to rewrite, actually, I'm going to write it as root 61 over 6 since I'm adding it to that fraction. I could even write this as 5 plus or minus the square root of 61 over 6. Okay. There's a variety of ways we can write this that are all correct. I don't think that 61, I don't think we can do anything nice with that to pull anything out of that radical. So I think this is the way we're going to write it. So there's our two solutions, 5 plus root 61 over 6 and 5 minus root 61 over 6. And I'm going to leave that one there. You can try graphing it. You can try plugging these values back into the original equation, and you'll find that they, if you're careful with your algebra when you expand everything, that this does indeed solve the equation. In other words, it's true. It's true that this equation 3x squared minus 5x minus 3 is equal to 0 when we put in either of those x values. So we could do another example, right? We could do another example. I could make up some numbers, do another example, 8x squared minus 13x plus 7 equals 0. And we would do all the same steps. Subtract that constant, find half of the coefficient of x and square it and add it to both sides, write it as a perfect square, and on and on and on, right? So we can do all these same steps, getting rid of any coefficient of x squared, all that stuff. When we have something where we're doing the same set of steps over and over and over again, a reasonable thought to have is, I can probably shortcut this with a formula. I can write down my steps instead of with numbers, with symbols, and kind of condense all that work into one little formula. Let me show you exactly what I mean by that. We are trying to solve equations like this. And what we just saw is, if we've got an equation like this, a good first step, if we can't factor it, is to multiply the whole thing by 1 over a, so that we get our x squared term without a coefficient. So this will now look like x squared plus b over a x plus c over a equals 0. Okay. The next thing we did was get that extra constant term over to the other side. So we've got x squared plus b over a x, right? The c over a minus c over a cancels, and over here I've got minus c over a. Now I look at this coefficient of x. It's b over a, but I want half of it. So this is going to be b over 2a. And I'm going to take that and I'm going to square it. And I have to add the same thing to the other side. Right? So far, so good. So on the left-hand side, remember I built this so that I could take this thing I'm squaring and simply add it in, right this side like this. I've constructed it to be a perfect square. And if I write x plus b over 2a times x plus b over 2a, what I'll get is what I'm looking at above, x squared plus b over a, x plus b over 2a all squared. Let's do some algebra on the right-hand side. So first thing I'll do is just square the whole thing. Looks like that, okay? Let's do another couple steps of algebra. I'm going to do this work off to the side again, so this computation doesn't get too ugly. So I've got two fractions here. I'm going to try to write them as a single fraction. So I'm going to write c over a. I want to have a common denominator. I want 4a squared. So I need to multiply the denominator by 4a, but I also have to multiply the top by 4a. And I'm still adding b squared over 4a squared. So what do we get? This, I've got on the numerator 4a times c, or negative c, so I'll have negative 4ac, and I've got plus b squared, and all of this is over 4a squared, and just by convention, I'm going to write this way. b squared minus 4ac all over 4a. Okay, so I'm going to take the square root of both sides. I get x plus b over 2a is equal to the square root. Whoops, this is equal to the plus or minus square root. Plus or minus. But I'm going to use this form that I just figured out up here. This thing on the right is equivalent to writing b squared minus 4ac all over 4a squared. Okay. Let's do some manipulations to this square root, again, off to the side. We've got the square root b squared minus 4ac all over 4a squared is equal to the square root of b squared minus 4ac all over the square root of 4a squared, which is the square root of b squared minus 4ac. The square root of 4a squared is simply 2a. Okay, so we've simplified that side somewhat. All right, now back to our main problem. I'm going to subtract b over 2a from both sides, minus b over 2a. So I get x is equal to negative b over 2a. Still got a plus or minus here. And I've got this thing that I worked out over here as equivalent to this big square root is b squared minus 4ac all over 2a. And now I'm simply going to write this as one fraction. They already have a common denominator. So I'm going to do all the signs in the numerator. We've got a negative b plus or minus the square root of b squared minus 4ac all over 2a, which might be a familiar formula to you. This is the formula part of the quadratic formula. So let's state it fully. So let's say something like given let's see. Let me say it a little differently. Let's say it this way: the solutions to ax squared plus bx plus c equals 0, where a, b, and c are real numbers. So this is just a little symbol to mean a, b, and c. This little backwards, this little squirrely e thing just means are in or are members of the set, and this r with the double line is just the real number. So all that means is where a, b, and c are numbers, are real numbers, and a is not 0. So the solutions to this with these conditions are given by x is equal to negative b plus or minus b squared minus 4ac all over 2a. Okay, so the quadratic formula is not just this x equals negative b plus or minus square root of b squared minus 4ac all over 2a. It's this whole idea. We have to understand what this formula is giving us. It's telling us that if we're given an equation to solve, ax squared plus bx plus c equals 0, where a is not 0 and they're all a, b, and c are all constants, that we can get the solutions simply by using this quadratic formula. So let's look at a couple of examples. For instance, if let's look at one of the first examples we looked at, x squared plus 5x plus 6 equal to 0. This was in an earlier video. And we factored this into x plus 2, x plus 3 equals 0 to find two solutions, x minus 2, sorry, x equals 2, or x equals, not 2, negative 2. Sorry, x equals negative 2 or x equals negative 3. All right, so we did that work previously. We could have also used this quadratic formula. We can always use the quadratic formula. Factoring is not always possible, or at least not always reasonable to do. Completing the square we can also always do, but it's a lot of steps. And really, completing the square just does this is completing the square kind of wrapped up in one. Instead of doing each step individually, there it is for us. So let's see what happens when we try to solve this using the quadratic formula. Looking at our original equation, we see that a equals 1, b equals 5, and c equals 6. And so plugging those numbers into this formula, we get x equal to negative b, so negative 5, plus or minus the square root of b squared, so 5 squared, or 25, minus 4 times 1 times 6, all over 2 times a. So in this case, over 2. Let's do the work inside. We get the square root of 25 minus 24 over 2. This is negative 5 plus or minus. Well, 25 minus 24 is 1. Square root of 1 is 1. So we get negative 5 plus or minus 1 over 2. So that looks like, let's write them out separately. We get negative 5 plus 1 over 2 and negative 5 minus 1 over 2. Negative 5 plus 1 over 2 is negative 4 over 2 or negative 2. Negative 5 minus 1 is negative 6 over 2 is negative 3. And so our two results, of course, show up the same, right? They have to. We did nothing wrong in either case. And so they better agree with each other. Otherwise, one of them is broken, or at least one of them is broken. Let's do one more example. Let's do x squared minus 2x plus 1 equals 0. Let's try solving this with the quadratic equation. So we know that the solutions are given by negative b. So b in this case is negative 2. So that's going to be 2 plus or minus b squared. So negative 2 squared is 4 minus 4 times a. A in this case is 1. C in this case is 1. And 2a is just 2 times 1, or 2. And we get that x is equal to 2 plus or minus. But notice we've got 4 minus 4, or 0. So 2 plus or minus 0 over 2, which is just 2 over 2, or 1, right? We had two answers, but they're plus 0 or minus 0, which in both cases does nothing. So we've got 2 over 2 is 1. We actually only get one answer out of this. Let's get some insight into why that might be. If we had factored this, x squared minus 2x plus 1 equals 0, this can be factored into x minus 1 times x minus 1 equals 0, or x minus 1 squared equals 0, which is plainly only solved when x equals 1. It only has one solution. Okay? And whoops. Let's do one more example, and then we'll look at all three of these on a graph. Let's do one more example. We've got, let's look at 2x squared plus x plus 2 equals 0. Again, we want x equals negative b plus or minus b squared minus 4ac all over 2a. So we've got x, that gives us our solutions. B in this case, let's write it down. A is 2, B is 1, C is 2. So B is 1, so we've got negative 1 plus or minus B squared. 1 squared is 1 minus 4 times 2 times 2 all over 2a, so all over 4. X is going to be equal to negative 1 plus or minus the square root of 1 minus 16, so negative 15 over 4. And we see immediately that this is not solvable unless we allow for complex numbers. So let's write this as I times root 15 over 4. So this will even give us our solutions when the solutions happen to be complex or imaginary, depending on how you want to, well, there are complex numbers. So we won't be dealing with that a ton in the near future, but we should know that happens. Notice we had 3 different situations here. We had 2 solutions right here, x equals -2, x equals -3. We had 1 solution, x equals 1, and we had we had 0, let's say, real solutions, 2 complex solutions, okay, in this last case. And what it all comes down to, those three conditions are, what happens to this square root? What happens to the square root of b squared minus 4ac, right? Let's look at the 3 different situations. In the first situation, our square root became 1, right? So if b squared minus 4ac is some positive number, we'll get 2 solutions, because you'll take the square root of a positive number which exists and you'll have plus that minus that, so you're going to get 2 different solutions. If b squared minus 4ac equals 0, you only get 1 solution, because as we saw, you have this plus or minus 0, but that doesn't actually give you 2 different answers. They give you the same thing, so you only end up with 1 solution. And then if b squared minus 4ac is less than 0, we get 0 solutions. But if we're dealing with complex numbers, we can say there are going to be 2 complex solutions, okay? But in terms of real solutions, you get 2 solutions, 1 solution, or 0 solutions. Let's go back to a graph to look at this. That first x squared plus 5x plus 6, notice our graph intersects the x-axis in 2 different places, at -3 and at -2. Those are the 2 solutions to that thing being equal to 0. The next one, which was x squared minus 2x plus 1, hits our graph in only 1 place, right? That's the 1 solution. When it's a perfect square, its graph just tips the x-axis and then turns around and goes the other direction. When there's 2 solutions, it hits 1 on the way down, turns around somewhere below the x-axis, and hits 1 on the way up. Or if it's inverted, that will be in the opposite direction. When there's no solutions, or our solutions are all complex numbers, we don't see complex numbers in this graph, right? Our x and y axis are both real numbers. You can graph complex numbers, but we're a long way off from doing that. For our purposes, we can't graph them, which means our solutions don't show up. So here's that graph we did that only had complex solutions. We were looking for where it's equal to 0. That would mean the y-coordinate is 0. And we look at this graph, there are no places where the y-coordinate is equal to 0. It's above the x-axis the whole time. And so that this is the graphical representation of what we were looking at in these numbers of solutions, right? Because this b squared minus 4ac tells us something important about our function, the number of solutions, which is important for a variety of reasons, we give it a special name, and you'll hear it referred to as the discriminant. This is used in a variety of places, but when we talk about quadratics, this is what we're usually referring to when we refer to the discriminant. Okay, that is it for this one. So we've now completed our methods we have for solving quadratics. In the first video, we looked at just taking square roots in the simplest cases, factoring when possible. You can complete the square, or just use the quadratic formula. And it's reasonable to think, well, why would I complete the square? The quadratic formula is the result of completing the square. And it's true. If I'm solving an equation, I'm not going to go through the steps of completing the square. I'm just going to use the quadratic formula if I don't think it's factorable or easily factorable. Completing the square, though, is a good method in other contexts where the quadratic formula won't work, when we're not just solving an equation. So it is still a good thing to understand how to do, because you'll find yourself doing it in other contexts. And so you should still practice that a few times, but we definitely want to be able to use the quadratic formula as well, knowing how to use it and when is appropriate to use it. When we're solving equations, of the form ax squared plus bx plus c equals 0, as I've got written on the top here. When we're solving those equations, the solutions are given by this formula. Okay, that is it, everybody. Thanks. I will see you next time.